All right. So now we're going to ask a slightly broader question. How many ways can I roll either a 4 or a 3? And when I say this, I mean roll 4 dice and then pair off 2 and have 2 of those that sum to either 4 or 3. Note that our goal is going to be 3 possible numbers, but I think after this example, you might see why 2 is enough for us to do here. So let's go ahead and get started. First of all, we're going to look at the different pairs that we have like we had this time. So the different pairs that we have are, there's one way to roll a 3. I can get a pair of a 1 and a 2. And then there's 2 ways to get a 4. I can either roll a 1 and a 3, or I can roll a 2 and a 2. But to approach this problem, and to kind of just handle this in general, first, let's just establish some general cases, or some general quantities maybe. Because we already saw what happens if I try to roll 2 different numbers and then a pair that's another number. We already saw what happened when I tried to roll a 1, 3 and a 2, 2, and that was some math. Turns out that there's actually a lot of different things that can happen, and they fall in a lot of different categories, so let's just give ourselves a little table to work with. So we already saw that to roll 2 different numbers, there's 302 ways. That's what we saw when we tried to see how many ways to roll a 1 and a 3. Totally independent of what the numbers are. That could be a 4 and a 6, it could be whatever. We also saw, I'll put this on the same line because it's another pair. We saw that to roll the same number twice, there were 171 ways. We also saw that to roll both a pair and then of 2 different numbers and then a pair of the same number that's distinct, there were 12 ways to do that. However, there's some other things that could happen. What if, and this is a situation we actually won't run into, but we can talk about it briefly. What if I need to roll 4 different numbers, like a 1, 3, or a 2 and a 5? Well, in this case, it's pretty easy. All the different dice are going to have to be different. I have 4 different things showing up. So it's going to be 4 choose 1, times 3 choose 1, times 2 choose 1, times 1 choose 1. That's going to be 24 different ways to do that. Okay. So we have that. So we've kind of handled what happens when we have 2 different numbers and then a pair that's different, of the same that's different, and then 2 different numbers and then 2 other different numbers. One that gets a couple that get rather tricky is, what if we have some overlap there? And here we're going to need to do a little bit of extra looking around. So one that will run into both of these cases. What if I want to roll a pair of 2 different numbers, and then I also want to roll a pair where one of them overlaps? So what could this look like? Well, I'm going to need 2 A's, and then at least 1 B. The other could be something else. Or I could have 3 A's and a B, or I could have 2 A's and 2 B's. All of those will accomplish this task. So what will that look like? That's going to be 4 choose 2 times 2 choose 1 times, there's 4 different options. And then we're going to have 4 choose 3 times 1 choose 1. And then we're going to have 4 choose 2 times 2 choose 2. And I already did the math to the side here. It turns out that when you sum this up, that's actually not too hard. This is going to be 6 times 2 times 4, which is 48. This is going to be 4, and then this is going to be 6. It ends up being a sum of 58. Okay, So we have that case. It's also possible that we might have A and B, and then it might be two different numbers, but still with some overlap. In that case, there's not a lot of different things that can happen. We can have A, B, C, and then something else. Or we could have two A's, a B, and a C. And I'm just going to put 3 times because we could have 2 A's, a B, and a C, or an A, 2 B's, and a C, or an A, a B, and 2 C's. Those are all going to be the same case. So how many different ways can we do this? Well, that's going to be 4 choose 1 times 3 choose 1 times 2 choose 1 times the last can be anything that's not an A, B, or C. And then in this case, we're choosing 2 dice to be the doubled one. And then we choose one of the remaining 2 to be the second value, and one of the remaining 1 to be the third value. And again, we have 3 of those. So we could say this is 6 times 2, that's 12. But we're multiplying that by 3 because there's 3 different ways that could happen. And then this is going to be 24 times 3. 4 times 3 times 2, yep. So that's 24 times 3, which is 72. And when you add all this up, it turns out that there's 108 ways. So that's going to be 36 plus 72, 108. So that's the number of ways that can happen. Okay. So we have all the pairs done. But inclusion-exclusion doesn't stop at pairs. It's possible that we can get 3 different things happening at once, or we're not going to move on to the 3 different numbers case, but in that case, it is possible to get 4 different values or 4 different combinations of the things that we want all at once. So in this case, when we're looking at 3 plus, we're going to just divide it up. For 3 plus, instead of breaking it up into all these cases, what we'll notice is that if I want to get 3 different combinations of numbers, I'm going to need to use all 4 dice to do it. So it's a question of what will those 4 different dice look like. They might all be different, in which case there's 24 ways to do it, just the number of permutations, sort of. Yeah, the number of permutations there. I might have 1 duplicate, and we already saw that somewhere. We saw it here. There's 12 different ways to do that. And I might have 2 pairs. In this case, my 3 different values I could get would be A plus A, B plus B, and A plus B. And if I have 2 pairs like that, there's 6 different ways to do it. Okay. So, and if we have 3 A's and a B, that would actually only have 2 different numbers it can make. It could only make A plus A and A plus B. I couldn't make B plus B. So that's all our stuff. Okay. So we have a whole bunch of stuff here, and now we're ready to actually tackle the question we have. So, and this is where inclusion-exclusion is going to come into play. So to answer this, I'm going to need to start by asking how many ways can I get a 1, 2? How many ways can I just get a 1 and 2? So I'm going to ask how many ways can I get one thing? Then I'm going to ask how many ways can I get 2 things? And then I'm going to ask how many ways can I get 3 things? And then I'll use inclusion or exclusion appropriately. So one thing, I might get a 1 and a 2. Those are 2 different numbers, so there's going to be 302 ways to get that. I might get a 1 and a 3. There are also 302 ways to get that. And then I might get a pair, a 2 and a 2. And there's 171 ways to do that. So I have all the different ways to get one thing. Now I want to think about the pairs. I could get 1, 2, and 1, 3. That's going to be this AB, AC case where there's 1 overlap. And we see that there's 108 ways to do that. I could get 1, 2, and 2, 2. at 2, 2. That is this case here where we have two different numbers and then two of the same numbers and there's an overlap. And there were 58 ways to do that. Or I could get 1, 3, and 2, 2, which we actually saw in the very first video, or the very second video. And that was, I believe, 12 different ways, if I recall correctly. Yeah. And then I asked myself, how many different ways could I get all three of these? So how many ways are there? Well, I would need to get I can get all three. First of all, I should check, is it possible to get all three? The answer is yes. I could get 1, 2, 2, 3, and that would do it. And that's actually the only thing that will get me all three, because that's also the only combination of three that I have here. So if I do that, then yes, I get 2 2s, I get a 1 and a 2, I get a 1 and a 3. So I guess to be very specific, it's not just enough to say what combination did I do. I need to identify the triple. So I'm identifying the triple. How many ways can I get 1, 2, 1, 3, and 2, 2 all at the same time? Since that's a 1, 2, 2, 3 pattern, that's going to be this case here where I have a repeated, and it's going to be 12. So to calculate my final answer, I'm going to add up all the different ways to get one of my values. I'm going to subtract all the different ways to get two different pairs at the same time. And then I'm going to add back all the different ways to get 3 different pairs at the same time. I have not done this in my calculator yet, but I'm about to. And it turns out that there are 609 different ways to get that result. So there we go. We saw that inclusion-exclusion can get a little bit tricky. We actually saw kind of both different approaches to dealing with inclusion-exclusion type problems. We saw the case where I could have maybe gone about some of these other things using inclusion-exclusion, but I found it easier to break it up into, I want to break this up into totally isolated cases and add them together. So we have those totally isolated cases, we add them together, but then when it came to combining different pairs of these, it was easier to use inclusion-exclusion. I counted how many different ways can I get one of these pairs, and then how many ways can I get 2 of these pairs, and then how many ways can I get 3 of these pairs. So there's a lot of counting, a lot of combinatorics in here, and this is all for just a little dice game. And what I think is interesting is it shows you how kind of unknowable the probability in this game is, because you have to do such complex calculations, which is really nice for a push your luck game where you kind of have to just go on your intuition rather than mathematical precision. So there you go. There's a little bit about combinatorics and counting in Cant Stop.